Download this code from codegive.com, link in the description below. Understanding and handling 204 keep alive client connections not handled properly and error 3507. The error message 204 keep alive client connections not handled properly combined with error code 3507 usually arises in environments with high concurrency where persistent HTTP connections, keep alive, are not being managed effectively. This often occurs in situations where a server is receiving more requests than it can handle concurrently or when the connection management logic has issues related to idle timeout, connection closure, or resource exhaustion. Let's break down this problem, understand the underlying concepts, and explore how to address it with code examples. 1. What are keep alive connections, HTTP persistent connections? HTTP keep alive, also known as HTTP persistent connections or HTTP connection reuse, is a feature that allows multiple HTTP requests and responses to be sent over a single TCP connection. Instead of opening a new TCP connection for each HTTP request, which is the default behavior in HTTP/1.0 without keep alive, the connection remains open after the first request is served, allowing subsequent requests to be processed over the same connection. This significantly reduces latency and overhead associated with establishing new TCP connections repeatedly. Benefits of keep alive ***. Reduced latency ** eliminates the need for TCP handshake for each request, reducing the time it takes to retrieve resources. Reduced server load ** less connection setup / teardown reduces server CPU and memory usage. Improved network efficiency ** fewer TCP segments and packets on the network. How keep alive works ** 1. The client sends an HTTP request with the connection, keep alive header. 2. The server, if configured to support keep alive, responds with connection, keep alive in its response. 3. The server keeps the connection open for a period of time, defined by keep alive timeout and max requests parameters. 4. The client can then send subsequent requests over the same connection without establishing a new one. 5. The connection is eventually closed after an idle timeout or when the server reaches the max requests limit or encounters an error. 2. Why 204 keep alive client connections not handled properly happens. The error message and the associated code 3507 indicates a problem in managing these persistent connections. Here's a breakdown of the common causes. Connection exhaustion ** The server might be reaching the limit of allowed concurrent connections, defined by OS or server settings like max_connections in Apache or worker_connections in Nginx. If the server is not properly closing or recycling idle keep alive connections, it can become overwhelmed. Idle timeout issues ** The server's idle timeout value, the time a connection can remain open without any activity, might be too long. Long idle timeouts can lead to resource wastage as connections are held open even when the client isn't sending requests. Incorrect connection closure ** The server might be closing connections prematurely or not handling connection closures gracefully. This can cause the client to attempt to send requests on a closed connection, leading to errors. Sometimes the server may not properly read the entire request or response before closing, resulting in data loss or unexpected behavior. Request handling issues * Problems within the request processing logic, example slow processing, blocking operations, memory leaks, can slow down the server's ability to handle new requests, leading to a backlog of keep alive connections. Load balancer issues * If you're using a load balancer, it might be configured with a different timeout value than your backend servers. If the load balancer closes a connection while the backend server is still keeping it open, it can cause problems. Code bugs. Bugs in the server-side code related to connection management, threading, or concurrency control can cause unexpected connection handling issues. Incorrect synchronization mechanisms or race conditions can lead to improper connection closure or resource leaks. 3. Diagnosing the problem. To effectively diagnose the issue, follow these steps. 1. Monitoring. Use server monitoring tools, like Top, Netstat, SS, Prometheus, Grafana, to monitor the number of active connections, CPU usage, memory usage, and network I/O. Look for spikes in these metrics that correlate with the occurrence of the error. Also monitor your server's error logs. 2. Logging. Enable detailed logging on your server. Log connection establishment, connection closure, request processing times, and any errors encountered during the connection life cycle. This can provide valuable clues about where the problem lies. 3. Network analysis. Use network analysis tools like Wireshark or Dump to capture network traffic and examine the HTTP headers and TCP packets. This can help you identify connection resets, premature closures, or other network-related issues. 4. Concurrency testing. Use load testing tools, like Apache Benchub, JMeter, Gatling, to simulate high traffic and concurrency. Observe how the server behaves under load and if the error 204 keep alive client connections not handled properly occurs. 5. Code review. Carefully review the server-side code related to connection handling, threading, and concurrency control. Look for potential race conditions, memory leaks, or incorrect synchronization mechanisms. 4. Solutions and code examples. Here are several approaches to address the 204 keep alive client connections not handled properly issue, with code examples demonstrating the principles. The specific solution will depend on the root cause of the problem. Example 1, handling connection timeout and max requests in Python, using socket and basic threading. Explanation max_requests defines the maximum number of requests a client can make over a single connection. idle_timeout specifies the maximum time, in seconds, a connection can remain idle before being closed. Crucially, con.setAmout, idle_timeout, sets a timeout on the socket, which is how the server detects the connection idleness. *handle_client, this function handles the logic for a single client connection. It receives data, processes the request, in this example, simulates it, and sends a response. It increments requests_served and checks against max_requests to limit the number of requests. The last_activity variable and time.time, last_activity idle_timeout condition control the idle timeout. *socket timeout the con.setAmout function sets a timeout on the socket. This is important because without a timeout, the con.reqv call would block indefinitely if the client sends no data. A socket.timeout exception is raised after the timeout period expires. *error handling the try, except block catches potential errors during communication and closes the connection gracefully. *threading each client connection is handled in a separate thread to allow the server to handle multiple clients concurrently. Thread.daemon equals true allows the main thread to exit even if the worker thread is still running. *connection, keep alive header the response includes the connection, keep alive header to indicate to the client that the server supports persistent connections. How to run *. 1. Save the code as a .py file, example server.py. 2. Run it from your terminal, python server.py. You can then test the server with a client like curl or a simple HTTP client program. For instance, example 2, using a web framework, Flask, Python. Flask handles connection management by default, but let's illustrate controlling timeouts and connection limits. Explanation asterisk. Flask uses the Werkzeug WSGI server by default, which manages keep alive connections. You can control request size limits with appconfig max_content_length to prevent denial of service attacks. The time.sleep simulates request processing. You would replace this with your actual application logic. To manage the number of concurrent connections, consider using a production-ready WSGI server like Gunicorn or UWSGI with Flask. Workers, number of worker processes, each worker can handle multiple threads. Threads, number of threads per worker. Timeout, maximum time a worker is allowed to process a request, seconds. By configuring these parameters, you can control the concurrency and timeouts to prevent connection exhaustion. Example 3, Node.js, Express, with timeout management. Explanation idle_timeout sets a timeout for idle connections. Headers_timeout sets a timeout for the server to receive the headers. req socket.set timeout sets the timeout for each individual request. req socket.on timeout handles the timeout event. The server sends a 408 request timeout response and destroys the socket. Destroying the socket is important to ensure that the connection is closed and resources are released. Example 4, Apache configuration, keep alive settings. Edit your Apache configuration file, usually httpd.conf or apache2.conf, and adjust the following directives within the virtual host section. Keep alive on enables persistent connections. Max keep alive requests the maximum number of requests allowed per persistent connection. Adjust this based on your application's traffic patterns. A reasonable value is typically between 50 and 200. Keep alive timeout the number of seconds the server will wait for a subsequent request on a persistent connection. A shorter timeout, example 5 to 10 seconds, can help free up resources more quickly. Longer timeouts can improve performance for frequently accessed resources. Example 5, nginx configuration, keep alive settings. Edit your nginx configuration file, usually nginx.conf, within the HTTP block. Keep alive _timeout the timeout for keep alive connections in seconds. Keep alive requests the maximum number of requests allowed per connection. General recommendations and best practices. Keep timeouts reasonable set appropriate keep alive timeout values in your server configuration, Apache, nginx, or in your application code, Node.js, Python, etc. Avoid overly long timeouts, which can tie up resources. Limit max requests set a max keep alive requests or equivalent limit on the number of requests allowed per connection. This prevents a single connection from monopolizing resources. Use a production-ready web server for production environments. Use robust web servers like Apache, nginx, Gunicorn, or UWSGI that are designed to handle high concurrency and connection management effectively. Load balancing if your application experiences high traffic, use a load balancer to distribute requests across multiple backend servers. This can prevent any single server from becoming overloaded. Ensure the load balancer's timeout settings are aligned with your backend servers. Asterisk connection pooling, database. If your application interacts with a database, use connection pooling to reuse database connections instead of establishing a new connection for each request. Properly configure the connection pool size and timeouts. Asterisk asynchronous I/O. Asterisk if your application performs I/O bound operations, example reading/writing files, making network requests, use asynchronous I/O to prevent blocking the main thread. This allows the server to handle other requests concurrently while waiting for I/O operations to complete. Python's asyncio and Node.js's event loop are examples of asynchronous I/O mechanisms. Asterisk regular monitoring and tuning. Asterisk continuously monitor your server's performance and adjust the keep alive settings and other configuration parameters as needed to optimize performance and prevent connection exhaustion. In summary, the 204 keep alive client connections not handled properly error signifies that your server is struggling to manage persistent HTTP connections effectively. By understanding the underlying concepts, diagnosing the root cause, and implementing the appropriate solutions, like adjusting timeouts, limiting max requests, using a load balancer, and improving code concurrency, you can resolve this issue and ensure your server can handle high traffic and concurrency efficiently. Remember that proper configuration, robust error handling, and continuous monitoring are crucial for maintaining a healthy and scalable web application. Good luck.